Here is a function that sums every element of a list, and it contains no loop at all. Instead, it calls itself. Today, recursion moves beyond numbers. We peel one element of a list, trust the function we are still writing to handle the rest, and build the answer back up. So far, recursion has lived on numbers, where a tidy mathematical definition translates straight into code. Now we move to non-numerical things. We will use lists, but the same patterns apply to any sequence of values, tuples, strings, and so on. Lists are the natural place to start because lists are themselves recursive structures. A list can hold elements that are lists, whose elements are lists, whose elements are lists, with no advanced limit on the depth. Without knowing in advance how deep the nesting goes, writing iterative code is possible, but very hard. The recursive version turns out to be far more intuitive in the long run. Maybe not the very first time you see it, but it is definitely easier to write and easier to read. The first problem to solve is summing all the elements of a list. Iteratively, we loop through each element and do something with it. Here is the loop version. Result starts at 0. For each element E in the list L, result increases by E. When the loop finishes, we return result. These are the state variables from last time. The loop variable E tracks which element we are on, and the result carries the running value. On the test list 30, 40, 50, result grows from 0 to 30 to 70 to 120, and the function returns 120. This works, and after everything we have learned so far, it is the natural way to think. Now we solve the same problem with no loop at all. Before writing any code, we walk the recursive idea through by hand. Take the list 10, 20, 30, 40, 50, 60, and ask for the sum of all its elements. That is the original problem. Pull out the first element, 10, and consider the remaining elements, the 20 onward, as a list of their own. If I knew the sum of everything from 20 onward, the sum of the original list would be 10 plus that sum. Notice what that remaining piece is. Summing the elements from 20 onward is exactly the same problem as before. It is the problem of summing a list. It just happens that the list is the original one minus its first element. We have taken our problem and produced the same problem again in a slightly smaller version, so we do it again. The shorter list is our new list. We extract its first element, 20, and consider everything after it as a new list. If I knew the sum of 30 through 60, I will add the 20 I extracted and have the sum. Keep going. Extract the 30, and if I knew the sum of 40, 50, and 60, I will add the 30 and have the answer. We keep peeling off one element and treating the remainder as a list, all the way down to a list with just one element in it. That is a trivially simple problem. If a list has one element, the sum of its elements is the value of that element. Here, 60. There is no need to keep dividing because we already know the answer. That is our base case. Now the result builds back up. The bottom call answers 60. The call that extracted the 50 passes up. 50 plus 60, 110. The call that extracted the 40 adds 40 to 110 and passes up 150. The call that extracted the 30 adds 30 to 150, giving 180. The call that extracted the 20 adds 20 to 180, giving 200. And the original question adds the 10 to the 200 we just figured out. The full sum is 210. That is the whole shape of recursion. Divide all the way down to the base case, then build the result back up. Now we write it in pieces. The function is called total recur. It takes in a list L and recursively figures out the sum of all its elements. First the base case, and there are two reasonable choices. The hand walkthrough stopped at a list of length 1. When the length of L is 1, picture the list holding just 50, no recursion is needed, and we return L at index 0, the 50. That is the sum. The shipped code uses the other choice, an even simpler base case. If L is the empty list, return 0. Both give the same answer on any non-empty list. On 30, 40, 50, both return 120. Only the empty list version also survives an empty list. The length 1 version will run off the end of it. The full function on screen uses the empty list. Next, the recursive step. We extract the first element, L, at index 0 and add it to something. In the example, the list is 30, 40, 50, longer than one element. We extract the 30 and add it to the sum of the 40 and the 50. That something is the same problem we are solving right now, only smaller. So the something becomes the very function we are writing. Total recur, called not on L, that will be the identical problem all over again, and the list will never shrink. But on L from index 1 onward, which removes the first element. That is the whole function. Nothing else to write, no loop. On the test list 30, 40, 50, it returns 120, the same answer the loop gave. Notice what we did. We wrote a function by assuming we had already written it correctly. That is a strange way to think, but it is essentially what recursion is. You trust yourself to write the function correctly, so that the recursive step leads to the base case, and the result builds back up. There is a lot of trust involved. Stepping through this code in Python Tutor on your own is excellent practice. Here is a slight modification to try. The function still takes a list as its parameter, but instead of summing the elements themselves, it sums the lengths of the elements. The test list holds 3 strings, a B, then C, then D, E, F, G, H. The function should add the length of the first string, 2 plus the length of the second, 1 plus the length of the third, 5, and 2 plus 1 plus 5 is 8. The skeleton keeps the shape we just built with 2 blanks to fill. Start with the base case, a list with 1 element in it. With 1 element left, the sum of the lengths is just the length of that element, the length of whatever string sits there. So the base case returns the length of L at index 0. For the recursive step, we take the length of the element we extracted, again the length of L at index 0, and add the recursive call total len recur on L from index 1 onward, which delivers the sum of the lengths of everybody else. It is fine to write the 2 terms in either order. We are just summing 2 values. Run it on the test list. 2 plus 1 plus 5, and the function prints 8, the total number of characters across all 3 strings. The pattern is identical to summing elements, only the work done at each step changed, from the element's value to the element's length. A natural question is whether the recursive version beats the classic loop on efficiency. It does not. The recursive function is slightly less efficient because each recursive call pays the overhead of an actual function call, while the loops plus equals uses a built-in operator that has been optimized to run fast. And when Python executes plus equals inside a loop, it is definitely not doing this recursion behind the scenes. For summing a flat list, the iterative algorithm is perfectly reasonable, more intuitive, and more in line with what we have been learning so far. The point of the recursive version is to make the pattern familiar on an easy problem, because the problem ahead, like lists nested inside lists, are the ones where recursion genuinely wins. The template from this video works for any sequence: base case, an empty list, or a list with a single element, where the answer is immediate. Pick whichever one covers the smallest input your function can receive. Recursive step. Do this element's share of the work, then call the function on the rest of the list. Never on the whole list or nothing shrinks. Then trust, assume the call on the smaller list is correct, and the answers assemble on the way back up. Summing a list needed no recursion. That was the point of practicing on it. The same peel and trust template is about to handle searching a list, and flattening lists nested inside lists where iteration becomes genuinely hard. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.